So I went to record a video for you of the Chapter 2, 28 to 40 evens, and a very sad thing happened. I think what happened is that this iPad that I'm using had some other videos of my hand writing on pieces of paper, doing other problems. And I didn't go through and delete the old videos. And these are old iPads that I have in the iPad cart here in room 202 at Rockbridge County High School, Lexington, Virginia, 24450. They don't have that much memory, so a few of those videos just gums the whole memory right up. And I think pretty early in the video, like a few seconds in, I ran out of memory, and I didn't realize it, and I just kept going. So what I have here for you now, this is all the stuff that I did. I got up to, let's see, number 34, and I pretty much finished number 34, although that's where I realized what had happened. So here's what I'm going to do. I don't know what would you do in this situation if you were me? I mean, I could just do the whole thing over again, but that pretty much makes me want to cry and curl up into a little ball on the floor. So I don't know if you can sympathize with that or not. I just really don't want to do them all again. So here's what I'm going to do. I've got all the work here. I'm just going to talk through this, and you can treat this, it's kind of like a solution manual, right? You can pause on this and look at the work, and I think a lot of these you probably did without too much trouble. So let's take a look. 28 was pretty straightforward, I think. You just had to, you were given these things. This, I think, one mistake that would be fairly common among first-year introductory physics students, such as yourselves, would be to maybe forget this negative sign. If the car, was this a car? I think it was a car. If the car is going in the positive direction, then the acceleration has to be negative. Now, the world that we live in, the universe that we live in, doesn't come with coordinates or number lines or axes attached to it. We, humans, come along, and for the purposes of our trying to understand things and do some math, we are the ones who say, well, here's an x-axis, let's make this the positive direction, and it's super conducive to our mathematical processes to have those numbers and coordinate systems and everything. But there's no right or wrong about it. There is a right or wrong about the agreement of things. So, for example, if this velocity here of the car is 24.6 meters per second in the positive direction and it's slowing down, then that acceleration is the negative direction. You could have them the other way around, but what you can't have is both of them being positive. If you made them both positive, then you do the math and you're going to get a negative time. So that's a cue or a clue to you, if you get a negative time, that you made some kind of mistake. And most likely it is a sign mistake that you made, that you forgot to make something negative that should be negative. So watch out for that. If you do it right, you should get positive 5 seconds. And then if you use this other equation here, you should get that the stopping distance is 61.5 meters. And here's the graphs of position versus time and velocity versus time. These are super important for you to understand. You could make either one of them first, I think. If you wanted to make the position time graph, I just said we're starting at position 0. That's an arbitrary choice. Just like I said before, the universe doesn't have number lines attached. We come along and do that. So I'm going to put my number line down so that the car starts at position 0, because why not? And it ends at position 61.5, or stops there, rather. And now the slope of this, it's moving forward, slowing down. So I'm thinking about, as I'm making this, I know it's going to be a piece of a parabola, because if it's a position time graph and we have constant acceleration, this has to be some piece of a parabola. So what kind of piece? There's a lot of different ways you can slice off a piece of a parabola. This one, I must be starting with a slope of 24.6 and ending with a slope of 0. So I know that it's that downward bending, and that would be the peak or the vertex of the parabola right there. I could also have just gone straight to this and made this one first, as these are the velocities. So I'm starting with a velocity of 24.6, going down to a velocity of 0. And I know that this is straight because I have constant acceleration. And I also know what the slope of it is. The slope of this little line segment right here is negative 4.92 meters per second squared, because the slope of velocity versus time is acceleration. Now, that really plays very, very nicely with what we are doing in calculus, right? The calculus of this is the slopes of these. Oh, look at that.
Attendance is back, attendance is back up, and please go on and get your attendance done as soon as possible. Thank you.
I have not done my attendance yet, but I'm not going to bail out on this video, so they'll have to wait. Anyway, our derivative sketching, that's what this is, right? Here's a graph, here's its derivative. So hopefully that will reinforce some of the things that we're doing in calculus. Number 30, same deal. I'm not going to talk about it too much. I had to convert my kilometers per hour to meters per second, and realized I just kind of set up this generic conversion factor that I'm always going to have to multiply by 1,000, divide by 3,600, which is the same as dividing by 3.6. That's how you get from kilometers per hour to meters per second. You don't have to memorize that. You can always just set this up, but that's my little shortcut for doing that. So I set the stuff up. I found this time. This is the slowing down. Probably going to get a speeding ticket here, 2.5 seconds. Same thing with the sign. Got to make sure that if these velocities are positive, that this is negative. And then here's my graphs. I started this one. I made this first, slowing down from 38 meters per second to 25 meters per second. And then I thought about here, okay, I must have a piece of a parabola that has a positive slope, 38, and then is decreasing in slope, so bending down to having a slope of 25, but definitely not getting anywhere near its peak like this one did. I'm not coming close to stopping here. I'm just kind of slowing down a little. Number 32, this crazy guy who got in a rocket-powered sled, not recommended. Don't try that at home. And this is what I found for his acceleration. I wrote it in scientific notation because I wanted to write the number 200 with two significant figures, and that's how you can do that. It would be negative, because if this is his forward velocity, he's slowing down, so that must be the opposite sign. And then here, when they asked in this problem, they asked for what is his acceleration in terms of g. So the acceleration due to gravity, if you have ever noticed this, I'm sure you have, that if you drop something, it goes down. That would be like the most crude, not crude, that's the wrong word, but that's the most like unnuanced description of what happens. You drop something, it goes down. But now, I mean, we're interested in more detail, more nuance about how exactly do things go down when you drop them. And you probably have noticed that when you drop something, well, when you release it, right at that instant you let go, it's got a velocity of 0, and then it gets faster as it goes down. So what is the acceleration? If something's getting faster, that means it's accelerating. And it turns out, maybe you remember this from some other science class or other, that things fall with an acceleration of 9.8 meters per second in the downward direction. And we call that number lowercase g. And so when we talk about, maybe you've heard before, like when a fighter pilot is doing some kind of training or just flying a fighter jet and like banks in some kind of turn or whatever, that they pull some number of g's. Well, that's because it takes acceleration to change the direction of their velocity, to change the magnitude or direction of their velocity. So if you're accelerating, one of the ways to quantify acceleration is as multiples of this. Why would we do that? Because when in 1g, like in our gravitational field where things fall with an acceleration of 9.8 meters per second squared, that's what we're used to. That's when you feel like sort of normal. You feel like your normal weight. But it's possible to put yourself in situations like on a roller coaster or in a fighter jet or in this rocket sled where you feel more or less than the usual gravitational field. And so that's one of the ways that we do this. So this 200, if you divide by 9.8, it gives you a multiple of how many G's this guy would feel. That's a lot. That's borderline, that's certainly like that amount of G's could kill you. Usually my understanding is around like 10 or 11 G's is what the human body can withstand without some kind of like risk of permanent damage. So I'm sure this guy did all sorts of training and whatever. This is why, well, lots of things to say about that, and we'll talk about them more. If you ever went on the Intimidator, I think it's called, some roller coaster at King's Dominion, or I think it's King's Dominion, or Six Flags maybe. That roller coaster, from what I've never been on it, but lots of students have told me about it. When you come down like the first big hill, there's like a turn at the bottom, and in that turn, you experience something like 4 Gs. And I've had students give all sorts of reports about the physiological things that happen for everything from like tunnel vision to losing color perception, to your vision going black and white, to completely blacking out. And these are all well understood things that happen when the human body experiences some like upwards of like 3-4 Gs. Weird things happen. All right, so there you go. And then here's where we ended up. So this was number 34, the red car, green car problem. This is set up as a system of equations, and I'll tell you what's going on here in just a sec. But first, how did we set this up? I made a little copy of the diagram here, and let me tell you what I'm trying to summarize, what information I'm trying to capture in this little diagram. So the red car is starting here, and this is the green car. And in this green car is going to do the same thing for both of these little instances. It's going to start with some velocity here and some acceleration, presumably speeding up in this direction. Could be slowing down, I don't know. And the red car is going to do two different things while this is doing the same thing. The first time it's going to go at this constant velocity of 5.6 meters per second. I had to convert from kilometers per hour to get that. And when it does go at that constant velocity, then the cars meet at 44.5 meters. But on the other hand, if it goes twice as fast at 11.1 meters per second, then the two cars meet here at this greater distance of 76.6 meters. Now both times, this car is going to do the same thing. So I set up two different sets of my variables, and I'm feeling like this is probably going to be a system of equations because they want me to find both the initial velocity and the acceleration of the green car in both these situations. Now what I was able to get, the useful information I can get here, two things. One is if I divide this distance by the constant velocity here, that gives me the time that it takes, right? And of course that's got to be the time that it takes the green car to get there also. And then if I take 220 and subtract 44.5, that also gives me the displacement. Now I made this negative because I just decided that I'm going to be real consistent calling this direction to the right positive. So then that means the green car going from here to here, that is a negative displacement. It ends up in a more negative position in that direction than to where it started. Then I did the same thing for when the red car is going 11.1. I found the time that it's going to take it to get there, going at constant velocity, and I found the displacement for the green car to get to that location. Okay, so what is the equation that relates these four variables? It's this one. So I wrote that down. Here's that equation with these numbers plugged in. Notice that there's two variables, the a and the vi, but I have two sets of information, right? And then I simplified those. I multiplied this out. There's my 7.95 vi equals this. And then I did this one and I wrote it right underneath. And then, right around when the video conked out on me, I was showing you something pretty cool about how to do this. And I'm going to show you again because I want you to know how to do this. So, how would you solve this system? This is not particularly well set up for elimination, although I guess you could just look at these two and say, well, I guess if I multiply this top equation by 6.9 and I multiply the bottom one by 7.95, then I could get those numbers to match up and I could do elimination. Sure, you could do that. You could also do substitution. You could solve for VI or A and then substitute in the other one. But I just want to give you one more technology trick. That's not a trick, it's a mathematical tool. So I'm going to do it using an augmented matrix and matrix math. So here's what I'm going to do. I need to make a matrix that is a 2 by 3 matrix. And in that matrix, I'm going to enter these coefficients. Numbers. This, 31.6, 7.95, negative 175.5, and then another row with these numbers in it. Now I've already done that, so I'll show you what that looks like. To do that, you need to go over to Math Edit in this one, and you type 2 and 3 there. So make a 2 by 3 matrix, and then you can see I already have the numbers entered in there. Okay, then I'm going to go back to my matrix menu. I would like to do some matrix math. I'm going to select here, and I'm going to scroll down to this option, this RREF. That is an initialism for, do you know the difference between an initialism and an acronym? Here's a fun fact for you. I only learned this. I'm very, let's say, sympathetic to language and the precision of language. It's something that I've acquired more and more of an appreciation for as I've gotten deeper into my life. But I do really appreciate little details of language and how language, I guess in the same way that math can be very precise, you know, I like the way that language can be very precise. So the difference between an initialism and an acronym, just in case you don't know, maybe you already know this, is that an initialism is something like this, RREF, and an acronym is something like NASA. Like, so NASA is the National I should have picked one that I knew what the letters stand for. I think it's National Aeronautics and Space Administration, something like that. You could look that up. But NASA is an acronym because we say it. We pronounce those letters. We don't say it's the NASA. We say NASA. So that's an acronym. But if we did call it the NASA, that's an initialism. So this, I don't call this REF. I say it's the RREF. This is reduced row echelon form. So I'm going to pull up that matrix operation. Oops, what happened? I messed it up. Let's see. So I'm going to go back to matrix math. Math. Scroll down again to that reduced row echelon form and hit enter. Oh, I think I'm doing it from the wrong place. I need to be back on the home screen. I need to get back to my home screen, and then I need to do that. Math. No, geez, I'm having a hard time here. So, all right, fourth time's charm. Matrix, math, scroll down, hit enter. There we go. So I need to bring this up on the home screen, and then I'm going to put in the name of this matrix A by hitting enter. Close my parentheses. You don't actually have to do that, but my Obsessive compulsion forces me to. And I'm going to hit enter. Now this, if you think about how we entered these numbers, those were the coefficients. So these are the new. What the calculator did, it did some like allowed some legal matrix operations to get these numbers to be like this little identity matrix. And here, now what that means, if this is a 1 right here, that's how many A's I have, and this is a 0, that's how many VI's I have. So this is actually, the first row here is the equation that just says A plus no V's, A equals this, and VI equals this. So those are the answers. And that is how far I got in the last video. So let me write those down. So notice that they're both negative. That makes sense. I was expecting that because this green car is starting in this direction, and it having a negative acceleration means that it's getting faster in the negative direction. If these two signs agree with each other, then you're going to be speeding up. Because, if that seems weird, that a negative acceleration could speed you up. Remember, this is like a slope. So 1 second later from right now, when this thing starts, we're going to be minus 2.46. That's what's going to happen to this velocity. So that'll be like negative 14 and change, right? Well, negative 14 and change, that's faster than this in the negative direction. If you're subtracting from a negative number, then the magnitude of that number is increasing. So that's just one way of doing that. Maybe you found another way, but I thought I'd show you that little matrix game. All right. And I'm just looking at the book here real quick and noticing that their answers are not the same as mine. So maybe I just need to hang out here for one more second with this problem and figure out if mine are kind of close. According to the book, I have the even answers here that I'm looking at. This should be negative 2.0, and this should be about negative, hold on one sec, they have it in kilometers per hour. If you had it in meters per second, it would be about 13.9 instead of 12.3. So what did I do? Let me double check my times here. So I have 44.5 divided by 5.6. So that's good. And then this one was 76.6 divided by 11.1. That time is good. Check my displacements here. This one we're going 220 minus 44.5. That's good. And here I'm going 220 minus 76.6. That's good. Okay. Let's see. Let me double check these. So 7.95 squared divided by 2 is 31.6. That's good. And that's just the same number there. Right? Yep, right. That's right. And then here, 6.9 squared divided by 2, 23.8. That's right. And then my matrix, I'm going to go into edit so I can see what I typed in there. 31.6, 0.95, 3.8. Jeez Louise, what did I do wrong? I do not know. Well, maybe you can see it. Maybe it's something real obvious. I do not. Let me see if let me just reread the problem and see if I pulled something out wrong. I didn't. So there's nothing wrong with any of the setup that I did. There might be, there could very well be something that I'm missing, an error that I made that I'm not seeing here. But the process here is 100% legit. And I apologize for not coming up with exactly the same answer in the book. Although I will tell you, I'm not, this doesn't sound like a lame excuse. We have discovered over the past years that every once in a while the book does have a wrong answer. I don't think that this is a case of that, but it could be. I could be messing something up. All right, so there we go. Moving on. So 36. A car moves along an x-axis through a distance of 900 meters, starting at rest and ending at rest. So it speeds up and then it slows down. Through the first quarter of that distance, its acceleration is 2.25 meters per second squared, and through the rest of the distance, its acceleration is negative 0.75 meters per second squared. Okay? Seems pretty easy. So through the first quarter of the distance, if I have a total of 900 meters, then a quarter of this, let's call this leg 1 and leg 2 of the little trip of this car. Let's write down our information. So for the first while, we are accelerating in the positive direction, and since we're also going in the positive direction, that will be speeding up, starting from rest. And for the second leg, we're going to be slowing down, and since we're still going in the positive direction, a negative acceleration will slow us down, and we're going to slow down to 0. And this is going to be the first quarter of it, so that's 225 meters, and this is the rest of it, which is going to be 675 meters. Right? That's the first quarter, that's the other 3 quarters. And they want to know what's the travel time and the maximum speed. So the travel time, I guess I have to find the time for both of those and add them up. So that looks like we got delta x equals 1/2 at squared plus vit. And, oh, I don't know the VI here. I guess I will. I can once, or sorry, the VF. Yes, whatever I find for the VF here, I can put over here for the initial velocity, right? Because it's going to speed up here from this initial velocity to some final velocity. I'll also have to find that. And then this is the same as this, right? Because when this leg finishes, this leg begins. All right, so I think I need this time first. Delta x is equal to 1/2 a t squared plus vit, and the vi is 0. So that's just this. So gonna have to find, oops, get out of here, quit. Gonna have to find 225, actually I need the square root of 225 over 2.25 over 2. That's about 7.07 seconds. And so how fast is this going to be going? What is this VI over here? This VI over here, if you're accelerating with this acceleration for this amount of time, then, and you're starting from 0, well, that's just this linear, that's what acceleration does. It ticks up this much. Your velocity is going to increase by that much for every second. So just need to multiply that by 2.25. So that's about 15.9 meters per second. And that is the answer for that. What's the maximum speed? It's going to speed up to this and then the rest of the way we're slowing down. And now that I have that, just like that's what happens to that velocity, well, now this is what happens to that velocity. So every second that goes by, this is going to decrease by that amount. So setting up this equation again, I just need to divide my initial velocity by that. That's how many seconds it's going to take for it to tick down by 0.75s back to 0. That's 21.2 seconds. Now I think I have all the answers here. I just need to put them together. So my times, I got 7.07. It's about 7.1 in this. So time total is going to be about 28.3 seconds. Uh, 36. And I think I might have done something here. I might have caused it. I'm checking the answers again, and once again I have messed something up. So let's see. This is. Let me just check this. I might have made an order of operations error there. Let me just do 225 over, and then half of that would be 1.125. Yeah, sorry. That's a real rookie mistake there. So this time is 14.1 seconds. And of course, that's going to change this. It's going to double it. And then that's going to double that time. So that's what happened there. Sorry. So that's 31.8. That's going to be my max speed. And then this is also 31.8. And that's going to double this time. And then when I add those up, I should get about 56. 56.5 or 6, something like that. That's the total time. And let me just make sure we got the right 31.8 meters per second for the max velocity. Yep, that's right. Sorry about that. Got to be careful with your order of operations. The calculator did exactly what I asked it to do. Human error. Where are we at now? Was that 36? No, 38. We have, if the maximum acceleration that's tolerable for passengers in a subway train is 1.34 meters per second squared, and subway stations are 806 meters apart, what's the maximum speed a subway train can attain between stations? What is the travel time between stations? If a subway train stops for 20 seconds at each station, what's the maximum average speed of the train from one startup to the next? Oh, you know what? Sorry. Were we supposed to make graphs for 36 here? Did I skip? Yeah, sorry. Let's do that real quick. Just saw the little graph part of this problem, too. They want x, v, and a versus t for the trip. Okay, so here, my position versus time. Here's what I know for sure. I'm starting here, and I'm ending at 900. Right? And here I'm speeding up. And then for the first quarter, right? So if this is like there's my 225. So when I get to there, that takes 14.1 seconds out of the total, so something like here. So it's going to be like a upward bending, bending. It's supposed to be parabolic. Upward bending parabola to there. And then after that, it's going to be slowing down. So it's like a piecewise thing with two parabolas joined together. But notice here, that getting into calculus stuff here, these two things, this transition happens with smooth. There's not a sharp corner here. Right here, the slope of this is 31.8. And right on the other side of this, when it transitions to this one, the slope is 31.8. It makes a smooth transition between those two parabolas, and that's important. All right, so there's my x versus t, my velocity versus time. I start at 0, and then I'm going to get up to 31.8, and then back down to 0. And I know time-wise, I could mark those on this axis if I wanted to. And I know that the slope of this is 2.25, and the slope of this is negative 0.75, so I tried to make an effort to make this steeper than that. And I know that this maximum velocity is 31.8 meters per second. And then my acceleration versus time. My acceleration for the first bit is positive 2.25, and then after that, after the first 14.1 seconds, my acceleration is negative, and that happens for a little bit longer time. If you want to put open circles on the ends of those, that's fine. We don't really fuss about that in physics. In reality, like this is kind of a little oversimplified. Something can't very, very abruptly change from having a velocity of positive this to negative this. It could happen in a very short amount of time, but there would have to be like a transition. And if we zoomed in on this, there would have to be like ultimately a little bit, tiny bit of a curve there. But we're just working in these idealized situations, so this is fine. Also okay if you just leave those as little sticks without the little balls on the end. All right, 38. If the maximum acceleration is tolerable, okay, so we got these subway stations. This is kind of like the last problem, I think. We are 806 meters apart. The maximum speed, if we make this symmetric and accelerate at our maximum rate for half that distance, and then for the other half, if we're going to come to a stop, we're going to have to get back to 0 there. So we'll accelerate all the way up to the halfway point, and then we'll just like turn things around and decelerate with that same maximum tolerable acceleration there. And what do we want to answer first? What's the maximum speed? Okay, so for part A, I can just look at this first half. That's halfway. So I'm starting with a velocity of 0. So there's my three things. And I want to know what is the maximum speed. That looks like a Vf squared equals Vi squared plus 2a delta x. So Vf squared is equal to, that's 0, that's 2a delta x. So I need to find square root of 2 times 1.34 times 403. That is about 32.9 meters per second. And that is the right answer. Yay. And B, what is the travel time between stations? Okay, well, if I find the time here, it's going to take the same amount of time to undo that velocity. So I could do that. There's different ways you can set this up now that we have 1, 2, 3, 4 of the 5 things. The easiest one is if you're going to make it up to this velocity with this acceleration, well, this is what's happening every second. It's increasing by 1.34. So if I take this and divide by that, that's the time. You can set up the equation if you want. That's this equation. Since that's 0, the time is just the velocity divided by the acceleration. And that's going to be about 24.5 seconds. So the time total, we got to get up to speed and then slow down, so it's going to take twice that. That's about 49 seconds. And part C is, if a subway train stops for 20 seconds at each station, what's the maximum average speed of the train? So average speed is just the total distance divided by the total time. This thing doesn't turn around, so the total distance is still only going in one direction, and that total distance is 806 meters. That has not changed. But the time now, it's the total time plus the 20 seconds that it's got to rest, that it stops there before it takes off again. It doesn't really have to rest, I guess. That was a silly thing to say. It needs to pick up some people, let some people off. Subways are kind of like elevators. Do you know subway and elevator etiquette? You, if you're waiting to get on the subway, you stand to the side of the doors and let all the people come off first, and then you get on. Same as an elevator, right? You don't stand like right in front of the door, and like when the door opens, the people are like, can we get off, please? You stand off to the side, and then you let the people come off first. You learned so much useful stuff in this class. So that's the max average speed. All right, last one. Number 40. Driving toward a traffic signal when it turns yellow. Your speed is the legal speed limit of 55 kilometers per hour. I'm going to go ahead and change that to meters per second. That's about 15.3 meters per second. And your best deceleration rate has the magnitude of 5.18. Your best reaction time to begin braking is 0.75 seconds. That's not the time that goes here, right? That's like an extra thing. So time, I'm going to say TR for reaction, is 0.75 seconds. And to avoid having the front of your car enter the intersection after the light turns red, should you brake or come to a stop, brake to a stop or continue to move at your constant speed, if the distance to the intersection and the duration of the yellow light are, and then we get two different situations. So for part A, I have the distance to the intersection is 40 meters, and the yellow light, we have 2.8 seconds to either make it there and keep going or stop. So we're going to have to check out what both of those possibilities are. So first, if we just keep going, are we going to make it there in time? That's pretty easy to figure out. We just keep going at our constant velocity for that much time. So if we go, then we just keep going at our constant velocity. Constant velocity times time is equal to our displacement. So let's see, what are the things that I know here? I want to figure out, if I do go, how long is it going to take me to get to here? And then I can compare that to how long the yellow light was. So my time is equal to delta x. I'm going 15.3. So that takes me 2.6 seconds. So this is good. So we can go if we want. Now what if we try to stop? Will that also work? If we try to stop, then let's see. My reaction time is going to be 0.75 seconds. So that means for 0.75 seconds, I'm going to keep going at my constant velocity. Not because I want to, but because that's how long it takes me to realize that the light has changed. So the first bit of distance that we go before we hit the brakes is about 11.5 meters. And then we hit the brakes, and let's see, so I have an acceleration of negative 5.18 meters per second squared. My initial velocity is 15.3 meters per second, and I need to come to a stop. So I need to figure out my distance here. That looks like our old buddy Vf squared equal to Vi squared plus 2a delta x. So that's 0 is equal to 15.3 squared plus 2 times negative 5.18 delta x. So the delta x is that square divided by that. So trying to make any more calculator errors today. And that's about 22.6 meters. Okay, so my total distance that took me to stop is the sum of these two, which looks like it would be 34.1. And that's less distance than how far the light was, so I can stop. So in this situation, I could keep going and I'd make it into the intersection, and I also have enough time with this, with my reaction time and that deceleration to stop safely. Great. So that's part A, and then part B, now we've got a new scenario with a shorter distance here and a shorter yellow light. So I just need to do the same analysis that I did here. What if I go? Well, during my reaction time, I'm still going to go 11.15 meters, right? Because I'm still going the same speed, so I'm still going to go that far. And then oh, wait a minute. Hold on. If we go, sorry. I was getting into the stop scenario already there. If I go, then I have 1.8 seconds. Actually, there's two different ways. I guess we could compare either way. Let me do it the other way. So what if I figured out, like, how far am I going to go in 1.8 seconds? So delta x is equal to, I'm going at 15.3 meters per second, and I'm going, sorry, that is the Vx, jeez, I'm on McGrath. That's the Vx, and I'm doing that for 1.8 seconds. So I could just say delta x is equal to Vx times t, which it is for constant velocity, and find that my delta x is the product of those two, 15.3 times 1.8. So that's only 27.5 meters. So I did this one. With this one I compared the time, and I found that the time was less than how much time I had, so I was good. Here I did it instead by comparing the distance. So in 1.8 seconds going at my constant velocity, I only go this far, which means I'm about 4.5 meters short of the intersection when the light turns. So that means if I do keep going, I'm going to enter the intersection after it has turned red. So no, you cannot go with these numbers. All right, what if we try to stop? Is that going to work? So if we stop, I've got the same situation here. So my delta x for my reaction time is still 11.5 meters, right? That's what this is, while I'm realizing that the light is yellow. And then I've got the same acceleration and the same initial velocity, the same final velocity. So it still takes me the same amount of distance here. I don't need to redo that. I probably didn't need to write those down again, I guess. So that still takes me that far. So that is not going to work because that is more than this. You can also do a time analysis of this if you want to and compare the times. But my stopping distance here is it's still that much. I guess I had that number already. I could have just compared that to the 32. That was silly that I redid that. Nope. In this case, this is not a fair yellow light because if you're 32 meters away and you're going the speed limit and that's how long the light is, you need to be able to stop, right? Or make it through, or both. So this yellow light needs to be longer. All right, there you have it.